In this video, let's discuss dynamic programming. First, let's say why we need dynamic programming and what it is that. Let's use fabulous number as example. Take a look at the formula fn equal to fn minus 2 plus fn minus 1 with seed value f0 equal to 0, f1 equal to 1. And based on this recurrence relation, we can quickly infer a series because every number is the sum of the previous two numbers except the first two. And such that we have f2 equal to 1, f3 equal to 2, and every number is equal to the sum of the previous number. And we can quickly write the recursive solution, right? This is the base case, and this is the recursive core. And to calculate the fabulous n, we need to get ready for fn minus 1, and also get ready for fabulous n minus 2. And for each this one, and the computer will recursively go to the invoke this function and with different parameters, right? And then do calculation. And then this is the very easy to write. This code is very easy to write. Recursive solution, very easy to write. And from here we can build the fabulous recursive tree for fabulous 5. To calculate fabulous 5, we need to have fabulous 4 and fabulous 3 already calculated. For each one, they have to go to the fabulous 1, fabulous 2, and each one we also need to recursive to calculate fabulous 2 and fabulous 3. Take a look at this recursive tree. I would like you to see what could be the problem. Then we find out, for example, fabulous 3 appear in the different places of this tree, right? And also the fabulous 2 has been recalculated for different places, right? And such that we see this recursive solution easy to write, but it's not efficient because some calculation has been have to be re-performed. Now the question is, can we save the computer runtime? Can we calculate this, do this fabulous calculation for smaller number just for once, but not repeated? And this is go to this code. With okay, since we wanted to calculate, we wanted to perform this fabulous for smaller number, and we wanted to just use it for once, we have to memorize in somewhere. And so this is the memorize based solution, and we define an array. M is array. We define array, use this array to remember for different n, right? If this is n, m, n, right? Then so we say that if you want to invoke this one, we say that if it is 0 and 1 base case, we have 0 and 1 has been already set up. And then if you want to invoke fn minus 2, if that is fn minus 2 doesn't exist, then we invoke that, right? And if that already exists, we just retrieve that. So it means in that case, this problem for fabulous calculate fabulous file, we say check for fabulous 4, and then check for fabulous 3 is the first time to do calculation, and then it will invoke fabulous 2, right? The first calculation, and once it's ready, then they got this one ready, and such that the fabulous for smaller number has been calculated before perform the big number and save somewhere. Save in the array to reuse that. The main approach of dynamic programming is recursive based. Hot answers to a sub-problem in a table can be used without recomputing. Dynamic programming can be formulated both via recursion and same results in a table. It's memorization, also called memorization. Typically, we first formulate a recursive solution and then turn it into recursion plus dynamic programming via the memorization or bottom-up. And we will show you. So this is a different approach to write the code. And this one is what we showed in the previous several slides. Use the fabulous example, right? We check if this number exists or not exist. If it exists, we use that. If not exist, then we do calculation. Bottom up, we'll show you example. We make this table. We fill the smaller number, one by one. Then we fill big number. Dynamic programming is a powerful algorithm design technique that has been widely applied to solve optimization problems, where we want to find the optimal solution to a given problem. This is a typical way. Sometimes, if the bigger problem cut into a smaller problem, and some smaller problem has been reused, some calculation has to be reperformed, and we want to make the runtime more efficient, we also like to use this dynamic programming approach. Dynamic programming like the divide and conquer method. Right? Since we see the sub problem, it reminds us the previous technique we discuss divide and conquer, and solve problems by combining solutions to sub problems. However, divide and conquer method is used to solve problems that can be partitioned into disjoint sub problems. Dynamic programming is used to solve problems which sub problems are often overlapped, with the feature in mind that sub-problems share sub-problems. We can use dynamic programming method to solve each sub-problem just once and then save its answer in a table, thereby avoiding the work of recomputing the answer every time it solves each sub-problems. When developing dynamic programming algorithm, we follow a sequence of 4 steps. Characterize the structure of optimal solution. This is very important. We have to find out what it is this optimal structure there. And we need to find out and what could the sub-problem can use the same approach to work on that or not. Because it's talk about the recursion. They use recursive-based approach. And recursive define the value of an optimal solution. So it means the calculate for big connection can be reduced to the calculation for smaller one. Right? And we recursively define that. And then we calculate the value of one optimal solution, typically in a bottom-up fashion. Construct the optimal solution from computed information, if we need. Now let's take a look how we follow the previous steps to solve a problem by using this dynamic programming technique. This is called RodCutting problem. Corresponding to in the industry, they have some specific company called steering company. They buy longer rod and with the price, right? And they sell it, the piece by piece they sell it. And the point is, they have different prices for rods of diverse lengths. For example, here, this is the rod length price table. If it is usually the length here, we talk about integer number, and here we assume the price also integer. Of course, you can use real number. And if the length 1, the rod of inch 1, the price is 1. The rod of length inch 2 has price 5. The rod of inch 3, which is 8, right? So the company, they buy the rod, for example, 10, right? And they bought this one with 30, for example, right? And actually they could get even more, cheap, the cheaper rod, and sell it, piece by piece, depending on different combination of, depending on different cards, the different placed card make a different number of rods with different pieces. The company can earn differently based on the price difference. Let's see one example, right? And of course here the question is how we can solve this problem, help this company to earn maximum. Given a rod of length n, we wanted to maximize the revenue by cutting up the rod into pieces. Of course, this cutting up is not randomly. We wanted to intelligently cut up the rod into pieces and selling each of pieces, based on the price, and the total add up for these pieces, rod piece selling, it is smaller, right? And then in such case they can earn more. Let's see, if we're given a 4 inches rod, what is the best solution to cut up? Let's say here, right? We say this is the, since it is inch, is 1 inch to second 1 inch, third 1 inch, fourth 1 inch, and each this one, let's say this 1 inch, right? And let's use index. Total, this is the 4 inches. And if no cut, if there's no cut, in that case, company will earn $9. If we have one cut, right? And this one cut can happen in different places. It can happen here or here or here, right? And you could have this one cut. Then in that case, if it's one cut, we have different solutions. For example, we also list here. If we have one cut such that the length inch 4 will, let's use this one, just to make sure, right? So let's use this one. Let's draw here. 0, 1, 2, 3, right? And the total 4 inches. Okay, so if we have 0 cut, right? No cut, 0 cut. In that case, with the company will earn the revenue is equal to line, right? If we have one cut, in that case, this one cut could happen in different positions. Maybe here, right? We cut here, or here, or here, right? Depending on different cut, we have different results. And for example, let's say we cut here, right? A solution, we have revenue is equal to what? Let's say all of this is 4, right? Is equal to the piece of inch 1, and we have this value. Let's have this value, and this is equal to 1 plus the length. This is what will remain, right? Because only have one cut. This is the only one cut here, and this is the piece of rod inch 3, so plus 8, we have line, right? And the same thing here, and the B solution is the B solution for one cut. So R4 is equal to, since you cut here, and in such that you have two pieces. Each one, it is P2 plus P2, right? Let's say this is the price for each inch. And then you have 5. And this is P1 plus P3, right? This one. Then you could have the one cut in this position, and this is C solution. So you have R4 equal to this piece with inch 3 plus P1 and equal to 9, right? This is for one cut. We could have 2 cuts. If you have 2 cuts, these 2 cuts could happen. Let's use different color. For example, you cut here, then one of the cut here, right? In such case, you will have, let's say, the cut 0. This is A solution. So this R4 equal to P1, because based on this cut, you have this piece, and also this piece, right? The 2 inches. You have P1 plus P1 plus P2. In that case, you have 7. You can see different cuts, or you have more cuts, but doesn't mean you will earn more. And for 2 cuts, you can also happen in the, let's use another color to represent that. Let's use this color. And it could be you cut here, but you cut here, right? It's the 2 cuts, and these 2 cuts we have R4 equal to 2 cuts make the different rods, and this is for piece 1, and this is piece 2 with inch 2. This is another piece. Is equal to P1 plus P2 plus P1. It's the same 7. And for these 2 cuts, of course, some of us may say, it could first cut happen here, and the second cut either places. We say that's fine. But in that case, it is still you make one rod, 2 rod once, and 1 rod of inch 2, right? And then you could also have 3 cuts. If it's 3 cuts. If it's 3 cuts for this a rod of inch 4, the 3 cuts will make what? Will make make 4 pieces. Each piece of rod inch 1, right? So in that case, we have R4 equal to P1 plus P1 plus P1 plus P1. In that case, we only have 4. And then compared to what we check here, this should be 10, right? Because P2 is 5, P2 is 5, it should be 10. In that case, we say, if this is if we wanted to, to find the maximum revenue for rod of inches 4, in that case, it is we need to have 1 cut. This cut in the middle of the rod, then in that case, make the best profit. Now the question is, if this given rod, which is kind of longer, very long, big rod, very long, is N, right? So how can we get Rn? How can we write a solution for that? How can we help the company for given any type of any number of N, you can help to calculate best cut. So in that case, this is an optimization problem, right? Now let's take a look to see what is the structure of this optimal solution. In the previous, what we analyze here is the same as what we wrote in the load. It's just the same. Once we write in the load, we follow the thinking and we vocalize what we think and write it down. It's more obvious. And now let's check for that. We say given a rod n, and we can have the first cut, right? Depending on the place of the first cut, and it will remaining the number, the rod of inches n minus I, right? Let's use this I as the represent the position in the first cut, and we have a revenue R given n equal to maximum of is low cut plus they do have a cut, and the first cut happen at the ith position. And then in that case it is the Rn equal to maximum Pn Ri plus Rn minus I. We could talk about this is the first cut. It doesn't mean it's the only cut, it's the first cut. And later they could have different cuts for this part or this part. They could have different cuts, right? Okay, what are we doing? Cut the rod into length I and n minus I. Only remainder n minus I can be full cut, recursive. So why you may say, why here we write Ri plus R n minus I, and why here when we talk about here we say it could be Pi plus R n minus I. The reason it is this solution we consider, you can recursively do that. This is the kind of repeated what we have here, right? We check out the first cut, and once I have a first cut, we say, okay, this whole thing here, we can sell that, and remaining here we can decide how to cut that. This is very obvious. So we need to define maximum revenue for log of size n Rn, and the revenue price for single log of length I, and this Rn is equal to maximum of Pn and Pi plus R n minus I. And we can simply find this one. In this case, this is based on, let's write it down here. This is maximized over odd I, but different cut, right? This is the structure for optimal solution. And if we cut log into length I and n minus I, and this piece, it is the complete piece, and this piece, we may need to have more cuts depending on which one will give us the best profit. And the n minus I can be recursive. There are many different choices of I. I could be from 1 through n, right? The position. And this is the formula we have over odd I. And we can write recursive top-down pseudocode. And this is the cut rod Pn. If n equal to 0, in that case, there's no rod, return 0. And Q signed to be infinity, negative infinity. And scan I, count I from 1 through n, because the first cut position could be from 1 through n. But we want to check, we want to find the maximum solution, the maximum cut for this first, what is the best position for first cut. And in that case, it's recursively invoke. And we say this is although it solves this problem, but it is a slow solution. It's not an efficient solution because this recursion, and take a look for root 4, we have to recalculate the 3. We have to recalculate, especially in this case, we have to recalculate for the 2 and 2, right? And even for 1 on root 1. And the reason it is, although this problem can be cast into the sub-problems, and the sub-problem overlap. Why? The reason it is, when you have n-i pieces, and when you reduce that, you have to recalculate that. Recursive solution is efficient since it repeatedly calculates a solution of the same sub-problem, overlapping sub-problem. Instead, solve each sub-problem only once and save its solution. Next time we encounter the sub-problem, look it up in a hash table or array. This is the memorization, or by using the recursive top-down solution. We will also talk about a second solution where we save the solution of sub-problems. Of increasing size in array, each time we will fall back on solution that obtained in the previous step and store in array, which is a bottom-up solution. And let's take a look. This is a cut rod with a memorization-based approach. And we initialize. We use R, right? And this is the array of R. And we initialize to be lective infinity. And we use memorize the cut rod. If fn greater than or equal to 0, in that case, we already filled some value. If n equal to 0, we get q equal to 0. We signed this n equal to 0. And what else? And we have q signed to be negative infinity because we want to make sure maximize what we earn, right? And then in that case, we compare the q from the previous position to have a first cut, and plus if it is I, we get the pi, this position for the first cut, then we recursively invoke what we have, this one. And this is memorized the cut rod works, and we give p as the price table for each specific rod of length, and we give m minus I as the given number, and r corresponding to revenue. And we can imagine here it is when I go to the large number, definitely it rely on what we have the smaller number for this r, right? This will be the smaller number for this r because it depending on n minus I, would have been recalculated. And here, this is the trick thing. It is we check if this specific element in this revenue array has been already calculated, right? Has a value there. And we could also have bottom-up cut rod solution. And in that case, we talk about, right, this is our third step and also corresponding to the fourth step. And first, we check if that is already known or memorized, right? We define this initialization. And we define a new array, initialize the first one to be 0. Then that after that it is, we fill And for example here, given this table, we have a revenue array, and we initialize of them, initialize the first element to be 0, and later you just in this case, maybe random number there, but the idea here it is we'll fill the later elements, and we check j from 1 is what we have 1, 2, 3, 4, right? It's 5, 6, 7, 8, and we check from 1 through n, and we first we have to be negative infinity, and we use I to scan from 0 through the j. And let's use this, let's trace that. Okay, so now when the j equal to 1, in this case j equal to 1, and the I from 1 to 1, right? In that case we calculate to maximize the q's in negative infinity, and the p1 plus r, 1 minus 1, right? So it means this is what we have. P1 is 1, so we put it here. And then let's check for R2. R2 is maximize negative infinity, or the first cut is in the 1's position, and we have this, or there's low cut, right? So the maximize of these two, and also corresponding to, if you j equal to 2, what do you have this one? Well, from 1 through 2, you have a cut at the 1's position, or that's low cut. And then we fill in that case we fill 5 in the previous solution. Then we fill the next one, which is j equal to 3. When the j equal to 3, we check for I equal to 1 and 2, right? And then in that case it is, if this is I equal to 1, the first cut is here, and this is what we have remaining, and that is R2. And in that case we have 6, right? So you have a first cut at 1's position is what we have, or the first cut in the second position, and there will be 5 plus R1, which is still 6. Or if that is the first cut in the third position, corresponding no cut in the rod 3, and in that case it is P3 plus R0, we have 8 is maximum number. And then we fill the next one and set to be negative infinity, and then in this, when the rod 4, this is same as what we discussed before, and we check if the rod cut is in the 1's position, and this is what we have. If the first cut in the second position, this is what we have. If the cut in the third position, this is what I have, and if it's no cut, right? We check each possible cases, and then we got number 10. This is exactly as what we have. We continue to fill this dynamic table, and this check for R5, and same thing here. We check first cut from here, and this remaining have 4. So this is the first cut at the 1st position, and this is the first cut at the 2nd position, and this is the first cut in the 3rd position, and this is the first cut in 4th position. This is corresponding to no cut at all. And you can see for each this one, what we have used exactly has been already in the dynamic table, right? So you have P1 plus what you have this one, or P2 plus what you have this one, or P3 plus what you have this one, or P4 plus this one, or this one P5. In that case, 13 is the best option. You continue check and follow this recursive, follow what we defined, use this recursive relation, right? This is exactly recursive relation, and by using the previous calculation, I filled each number, even the last one, have rod 10, and we check for each different cut, first cut, right? We took a first cut. What is position for first cut? And later, this one may, depending on the number of cut for each specific, sub-problem solution. And you can see this is the sub-problems. And each, this sub-problem, they do have some overlap, right? But once we use this dynamic table, once we fill this dynamic table from the lower index to higher index, it's also called the bottom-up way to fill the dynamic table. We got the solution ready for the smaller cases, and the solution for the smaller cases will be useful for the solution for big cases, right? This is what we talk about, the bottom-up based approach for dynamic table. And previously, we also show you the memorization-based top-down approach, right? So now we can see here, this is what we have to solve for ROD 4, right? Find the best cut for ROD 4. This is recursion-based solution. Now, this is what we have. We need to fill each table here. We really don't need to recalculate for each sub-problem. We reuse that. We reuse the value from that. And you may ask, what is runtime for this one? And we see the number of edges will be the runtime. Same thing here. And from here, we talk about recursive tree, and usually we have 2 to the power of n, right? In this case, we have a less. This total, it is a number of edges. And the worst case is just n to the power of 2, right? N squared. N O is, right? This is the worst case, even that one. Okay, now let's check exactly. The runtime is O n squared. Runtime is compilation of number of items in table n and work per term n. The work per item, because of the maximum operation needed even if the table is filled. And we will just take values from the table is proportional to n as in the number of edges in graph. That's it. I think this is what we would like to cover for this study. Thank you for the listening.